Good day, everybody. Thank you very much for joining us for our presentation today on the new features in FLAC3D version 9. My name is David Dugagne, and I'll be hosting. And today our main presenters are Zhao Cheng, who is our product manager for FLAC3D, and Jim Hazzard, who is our software manager. So we are taking questions today, and if you could enter your questions in the dialogue shown here in yellow, just take them in, hit send, and at the end of the presentation, we will take up any questions that you might have.
Okay, this is Jim. Thanks everybody for joining, and welcome to the FLAC3D version 9 webinar. This is just an outline of what we're going to talk about, the main features that we're going to hit upon. So starting from the top left, seriously faster. We do strive continually to make things faster and improve the performance. We'll talk a little bit about that. We've also managed to speed up some of the dynamic analysis. A couple of new features, zone joints. I'll talk about that towards the end. Nonlinear structures, and by structures I mean liners and shells and beams and piles. Now we'll talk about the new and improved constitutive models and the improved user interface. And then, as always, we like to emphasize the power and flexibility of FLAC3D through the scripting and command-driven interface that allows you to do very interesting things. But we'll talk a little bit about that as well. So the first point here is about the faster. And again, we're always trying to make things faster and improve the performance. The subcategories here are improving static and dynamic analyses, speeding up the fluid and thermal calculations. We have a new type of damping for dynamics, which helps speed things up a lot. Some speed ups in the plotting and some of the other commands that were not previously multi-threaded that now are. And also some speed ups in the save and restore and in the fish. So we'll just dig into the details a little bit more here. So the main thing here is the performance in general. We've done some optimization of the way that the cycling works, and we're able to speed up the convergence to a solution quite significantly. So if you're running a static analysis, you can get to the steady state solution roughly 2 to 3 times faster than you used to be able to in version 7. This is obviously model dependent, but we've run a lot of real world models and found that you can hit the convergence and reach the solved state in general 2 to 3 times faster than you used to be able to, and this is significant. The same sort of logic was used to speed up to increase the dynamic time step. And so again, if you're trying to solve to a given dynamic time, you can get there 2 to 3 times faster because the time step is now larger. So that's just the general mechanical calculations. We've also been working on speeding up the fluid and the thermal calculations. And the main strategy here was to introduce better implicit solvers. You may or may not know there has always been an implicit solver built into FLAC3D for fluid and thermal. That solver didn't actually work particularly well. And so we've introduced a new or several different types of new implicit solvers. And these go significantly faster than the previous one that we had here. So this is an example, a thermal example, and this is a nuclear waste type of problem. And so when they do these types of problems, they're often looking at very long time scales. In this particular case, out to 10,000 years. And so you can imagine running this explicitly with a small time step would take basically forever. And so being able to slot in this new implicit solver is a significant saving. So you can see in version 7, this would have taken you 43 hours, and in version 9, this takes you approximately 25 minutes. This was a temperature example. We've also put in the new implicit solvers for fluid flow. Currently, it's only working for saturated fluid flow, but we're very close to having it working for partially saturated fluid flow too, and I'll talk about that a bit at the end. There's also been some improvements in the plotting. The ability to plot groups with the zones is way faster than it used to be. Some of the commands that were not previously multi-threaded now are. So you can see some speed ups, again, not related to the calculations, but even just in executing some of these commands. Some aspects of the saving and restoring are faster, and there are some improvements to the fish splitting, which allows you to do multi-threaded fish. For dynamic analysis, as I mentioned, we changed the underlying logic a little bit so that you can have larger time steps. And so this is one thing that will speed up a dynamic analysis. We've also added a new type of damping. So for those of you that do dynamic analyses, you will know that if you use Rayleigh damping, this can significantly decrease your time step and slow down your simulation. With this new type of Maxwell damping, it provides the same sort of functionality without decreasing your time step. And so in this case, depending on how much damping you need, you can get very significant speed ups by using this Maxwell damping instead of Rayleigh damping. And now I think it's time for Zhao to talk about the details here.
Just before we do that, we're going to ask everybody to participate in a couple of polls. So first up, we're going to ask you if you could please select all that apply, of which of the following industries best describe your background. So we'll just let that go for a little bit. Great, thank you everybody. So I'm going to close this poll, and we're going to ask you now what your background is or experience using FLAC3D. And if you select one of these, just to give us a little bit of background about your background. And finally, what are you most looking forward to in FLAC3D 9? If you could select one of the following. Great, thank you again for everybody who participated. And we will share those when we distribute the presentation after the webinar. Thank you.
So let's go back to the Maxwell damping. So in very large FLAC3D simulations, so stiffness proportional or Rayleigh damping can be impractical because it significantly reduces the dynamic time steps. However, without stiffness proportional damping, high frequencies are noisy, so analysis results are questionable. So if we look at these two figures, the above figures is without Rayleigh damping, we can see a lot of noises. And with Rayleigh damping, 5% damping ratio, so the results are reduce that noises. So from FLAC3D version 9, we introduced a new damping called Maxwell damping. So by using more than one Maxwell components, usually we use 3 parallel to the constitutive model, and the frequency range can have relatively constant damping that can be obtained. So if we look at this figure, we have 3 dash lines. Each dash line is an individual Maxwell component. So if we look at one of them, so the damping ratio is frequency dependent. However, with the combine of the 3 dash lines, we have the combined damping ratio represented by this red line. So we can see that we almost have a constant 5% damping ratio in a wide range of frequency. For example, in this figure from 0.5 Hertz to 25 Hertz. So in FLAC3D version 9, we implemented Maxwell damping to zones, structure elements, as well as deformable structure links. So this example is a 1D site response. So we compare Maxwell damping with deep soil viscose result, which based on the frequency domain. result. And also compare with the FLAC3D using Rayleigh damping. So the first figure is with the input motion of normal gear. You can see that all three methods have very close result. And however, if the input motion is non-harmonic motion, this motion has more high frequency content. We can see that FLAC3D Maxwell damping actually is closer to the deep soil viscose because Rayleigh damping was overly damped at high frequency range. So generally, in FLAC3D, it's very easy to input the Maxwell damping. We just using this command, for example, zone dynamic damping Maxwell and 3 parameters. These parameters we already calibrate for you, so you can only choose which your target damping ratio. So generally, the response performance of Maxwell damping is as well as Rayleigh damping. However, it overcomes Rayleigh damping's shortcomings, that is, dramatically reduced time step and overly damped for high frequency. And Maxwell damping have no these shortcomings. In general, the dynamic time step of Maxwell damping could be 10 to 200 times of that Rayleigh damping. For example, for some large soil structure interaction dynamic analysis, and the time required wants to be 2 months. Right now, using Maxwell damping, this can be finished in less than 10 hours. That's huge progress. Okay, next I will talk about some new and improved constitutive models in FLAC3D. So in version 9, we have improved plastic hardening model and improved ubiquitous anisotropic model. We added 3 new constitutive models, that is conformal result, or sometimes we call combo model, and also plastic damage concrete model, and vomicysis model with kinematic hardening. So far, FLAC3D version 9 has 38 mechanical constitutive models, including 11 creep models and many user-defined models. So first, we talk about the plastic hardening model improvement. In version 7, the algorithm was based on Band's 2007 algorithm on small strain hysteric loop. For this algorithm has such shortcomings because it has overshooting for nested hysteric loops, and we thus add a note in the documentation say that this model may be not used for dynamic analysis. However, in version 7, we updated the small strain hysteric loop using a new brick algorithm. So using this algorithm, we remove that shortcomings, and we will show some examples later. So this update enables plastic hardening with small strain FLAC, a more practical dynamic model. So here example to compare the old algorithm and the new algorithm. Let's check the bottom 2 figures with assumed figures. So the blue line is a monotonic loading path, and the red line is monotonic loading first, and then unloading, and then reloading. During the reloading, we have a very small unloading and reloading. The problem of the old algorithm is that when the hysteric loops, back to the monotonic path, actually it's not, reach the original unloading point. So if we look at the new algorithm, and then the nested hysteric loops, can be simulated perfectly. Here is another example to compare the old and the new algorithm. So this, again, the 1D set response dynamic analysis. So if we check the bottom two figures, which is a shear strain versus shear strain figures. So with old algorithm, it's not quite good, to simulate the nested hysteric loops. And if we check the upper two figures, that is the acceleration history at the surface. We can see that the maximum acceleration is quite different, between the old and the new algorithm. The difference could be 25%. So the next improvement is ubiquitous anisotropic model. So in version 7, this model only has matrix is anisotropic elasticity. And from version 9, this model include both the anisotropic elasticity and Moore Coulomb law to the matrix. So this model is suitable for the cross elasticity material showed, for example, in this figure. And then we do some verification for this ubiquitous anisotropic model. So we do the verification by degenerate this model. For example, the first figure to the anisotropic elasticity by input a very large cohesion to the matrix and a very large cohesion to the joint also. So generally, this model will be generated to anisotropic elasticity. And then, so we can compare the result to the analytical result. Okay, that's perfectly matched. And the second figure is degenerated this model to ubiquitous joint, and then we can have some verification, and then so on and so forth. Okay, let's now talk about the new constitutive models in FLAC3D version 9. The first is a columnar basalt model. So this model can deal with up to 4 arbitrary orientations of weakness, or sometimes we call ubiquitous joint. So this model has anisotropic elasticity matrix, and also for the strain hardening, softening, Moore Coulomb envelope, and the tension cutoff for the matrix, and also strain hardening, softening for the joints, and also have a amplification factor can be applied to the joint dilation that depends on the angle between set direction. And very important, this model also has creep options on weak planes. So this model can be used for multi-jointed rock mass. For example, the columnar basalt showed in the figures, in this slide. So this example application of this model to the tunnel excavation. So in this model, we have 3 sets of joints, and then set 3 actually have a deep angle, always 90 degrees, of the first one. And we have the second joint just out of plane direction. So this example shows the effect of orientation of joints, to the deformation of tunnel. The next example is using this model for some valley creep deformation. So just remember that this model can have creep option along the weakness planes. Okay. The next new constitutive model in FLAC3D version 9 is a plastic damage concrete model. So this model can have damage development in both extension and compression directions. The damage is based on fracture energy and the modulus degradation in continuum damage mechanics. So this model has a yield surface compatible to our classical Moore Coulomb yield surface criteria. Okay. So if we check these figures, the first column is a uniaxial load in the compression direction. So the upper figure is a load versus the total strength, and the bottom versus the only plastic strength. So in the compression direction, we have the hardening stage from A to B, and then have the strength softening stage from B to D. And the second column is the extension uniaxial extension behavior. The difference between the compression and extension is that from the compression we have hardening and then softening, but in the extension direction we usually have strength softening immediately after peak strength. The last figure shows the yield lockers in biaxial strain plane. So from A to B, that's actually the tensile yield line. From B to C, that's the Moore Coulomb shear yield line. From C to D, that's the Druck-Prager yield line. So in this figure, the left, we compared the FLAC3D model to some experimental data in both uniaxial compression and uniaxial tension directions. We can see that this model has a very good match with the experiment. And the second, we will show a video of the concrete beam, which seated on two supports and subjected to two line load, and then they have some reinforcement bar, inside the beam. So let's see the simulations. So we can see some crack develop, at the bottom of the beam, and then the crack can, linked, from the support to the load position. Okay, this is the concrete model. Next, we are talking about the von Mises model. Generally, in FLAC3D, we deal with the geomaterial. That's generally the soil and rock. But however, in mining and geotech engineering, we still, have some mental structures. For example, this shear pile. So I think it's necessary to add a separate von Mises model with optional kinematic hardening. So for this model implementation, actually we will use this model for the nonlinear structures. Jim will talk about this nonlinear structure right now. Yeah.
Okay, so thanks for the introduction here. One of the big new features in FLAC3D version 9 is these nonlinear structures. And again, by structures, I mean shells, plates, liners, beams, piles, and so on. And by nonlinear, I mean instead of them being perfectly elastic, they now have the ability to elastic and fail, which is something in general we were not able to do in version 7. And so what we have is at the moment we have three different possible constitutive models for these elements. So instead of just being elastic like they were in the past, you could make them von Mises, as just discussed, Moore Coulomb, or Moore Coulomb with strain softening. And then by using these different constitutive models, relevant quantities are calculated at integration points, and so then you can get a sort of distribution of stresses and so on across the elements. So here's just an example of what that might look like. The beam elements are on the left. They could have rectangular or circular cross-section, and these red squares are showing you the integration points. The user has the ability to set the number of integration points, and obviously the more points you put in, the more accurate your solution, and also the more points you put in, the slower it's going to go. So as always, it's a balance between accuracy and speed. But I think the default is something like shown in this picture here. You can get a pretty accurate plastic behavior for these beams. And then the shell element on the right here, those are generally three-noded triangles, and then with some nominal thickness. And so then we actually have some number of integration points through the thickness and also along the triangle. So I think in this case, the default here is actually 9 integration points. Okay. So then it's just a couple of simple examples. This is a beam element. It's a rectangular cross-section on the left and a circular cross-section on the right, subjected to a 3-point bending test. What you can see is the force initially increases elastically, and we're showing the deformation on the x-axis here, and then eventually you get to the point where some of these Gauss points start to yield, and so you can see the curvature there as it sort of tends towards something that becomes eventually perfectly plastic, and then you get the formation of this plastic hinge, and it can no longer support any more load. Now, if you've used these kind of things before in version 7, you'll know that it was possible to simulate a plastic hinge. What's different about this is that you have this more sort of distributed failure. So you can see in the plot of the beam itself, there's parts that are never yielded, parts that are partially yielded, and parts that are fully yielded. And so instead of just the quick formation of this plastic hinge, you have a more distributed failure pattern, which is more realistic. For the shell elements, it gets even more interesting because there was no concept of a plastic hinge for these shell elements. And so adding this plasticity is really a big step forward for us. And so here's just another example. This is a square plate supported at the edges, some pressure applied to it. So yeah, let's hit the movie here. So again, it starts out behaving elastically. And then again, what you can see is this sort of gradual accumulation of failure here. So the red is sort of partially yielded elements, and the purple is the sort of fully yielded elements. And so you can see how it sort of becomes a kind of gradual failure, and then eventually the whole thing goes plastic so that it can't support any more load. So you can do some really interesting problems with these new nonlinear elements. And then here's a more realistic example. This actually combines a couple of the things we've talked about already. This is a model of the base of a wind turbine. It's using the concrete model that we talked about, and also has a whole bunch of reinforcing bars in it that are simulated with these nonlinear beams that we just talked about. So this encompasses a couple of the new features that we've been talking about. It was a very interesting model. They subjected this base to various stresses to simulate the effect of the wind turbine sitting on top. And what you can see here on the right-hand plot is a plot of the strains that occur after some set of stresses have been applied. And so you can see this sort of crack-like behavior. You know, those blue lines are showing you where there's very high strains in it. And it's looking like cracks are forming in this reinforced concrete material. And so this is the kind of stuff you can now do in version 9 that we could not do previously in version 7.
So let's talk about the new user interface. The most apparent change in FLAC3D version 9 is a new user interface. So we reorganized the user interface to make it more flexible. So in these new versions, we can split new windows. I will show this later. So generally from this slide, we have 7 areas. So number 1, main menu. Number 2, project pane. And number 3, command console. And the number 4, content workspace. So in this workspace, we can split different windows, you know, horizontally or vertically. Okay, and the number 5, toolers and the help panel. And number 6, layout toggles to hide. And number 7, status bar. And we have some many plot items improvement. For example, we have the user-defined contour ramp, so we can specify different formats and precision of the contour legend. So we can swap axis for table and profile chart. So we have options to add minor grid lines to charts. We have improved log scale for charts, and we have option to omit past dates when plotting yield dates. And we add a lot of more contours or histories. For example, contours of factor safety showed in this slide, and others, for example, structure node acceleration. So we have improved sketch. So from FLAC3D version 9, we renamed extrusion in FLAC3D version 7, and right now we name it to sketch because we have FLAC3D and FLAC2D. We try to avoid the confusing. So in this sketch, we have ruler and background grid. We have slope and tunnel wizard, and we can revolve a 2D sketch along a vertical or horizontal axis. And most important, we can extrude the sketch along a curved path. I will show examples later. And in FLAC3D version 9, we added the material dialog, so we can define and interactively specify material properties and create, and then import, export material properties in a built-in property database. So let's open FLAC3D example first. I just opened a tailing dam project. So this is a new user interface. So we have menu, we have the project panel on the left. So we have the list of data files, we have a list of plots, and then we have saved states and sketch states. So in the main workspace, we can select what we want. For example, we can select a model pane. Okay, we can select. We can create a new data file, whatever. Okay, we can change to some recent plot. Okay. The most important, we can split the windows. For example, we split left. Okay, we can open the data file in the left window, and we can we can adjust the size of the windows. And then in each windows, we can again have split. For example, we split this below, and then we opened the below windows, for example, to some other plots. So this is just to show the tailing dam. So this is quite flexible and most welcome features in FLAC3D version 9. So let's close the windows and then just focus on this contour first. In FLAC3D version 9, we have more built-in contour ramps, so you can choose from, for example, this one, and this one, okay? And we can actually define the ramps for ourselves. For example, I want to customize color ramp, and then we can choose this white color to some different color, and then we choose the second color to another different color, and then we can have our own, customized color map. Okay. The second improvement is to the legend of the contour. So if we go to the attribute text of the contour, we go to the legend, we go to the contour. So first we can change the position from the 2 to more with more digits. Okay. In FLAC3D version 9, the default digit is 2 digits precision. We can also change the format from scientific to decimal. For example, this one, okay? And the next features, we opened another project file. For example, this 1D consolidation examples. So for these examples, we have the consolidation simulation with soft soil model and a soft soil creep model. So we compare the different results between with or without creep. So, but for here, I want to show that, for these figures, we have the exact pressure with the depth. Some visitors want to say that, depth should be vertical. So how can we do that? In version 9, it's just one click. So if you look at the table attributes, we have a checkbox, swap axis. So just click that, and then this, we have the depth just vertically, okay? And then next is the log scale. So for these histories, we have the settlement versus time. If we want the time to be log scale, so we just can change the axis 1 to log scale. So we can see that this, apparently is a log scale because it's not uniform, okay? To make it more clear, we can check the grid and the minor one. So we can see clear this is a log scale, okay? This is the improvement in plot atoms in version 9. And next is extrusion. So we open another example. For example, this one. If we go to the new sketch state, we input a name A. So we can see that we have some rulers and background grid. We introduce some wizard on tunnel and slope wizard. For example, for slope wizard, we can have some different simple slope and bench slope, and let's using this bench one to show examples. So right now we have the bench, okay? So if we mesh all polygons, okay, and then we can automatically set the size, for example, to 1, okay? I will using this tool, extrude by rotation. For example, we have the size 20, and then we have offset from axis, for example, 10. We click OK, and then we will have the grid with the rotation along the sketch, okay? This is the example number 1. If we have another example to show extrusion along a curved path, so we have a new sketch set. We give a name A, and then we go to the tunnel wizard. For example, this one we have circular, we have rectangular, or some complicated shape. For example, this one, we choose this one. We will have a tunnel wizard, okay? So we mesh to this tunnel and then change the size to 1. Okay, this is the mesh in the front view. If we go to the bottom view, okay, we can change the position to, for example, 100, okay? And then we split the zone numbers to 100. And then we add some control point. For example, first one, second one, third one. We move this control point to some position, so we can exactly set the position of this control point. For here, I just make a simple example, okay? And then after this, we click the line and then make the line from line to curve, okay? And then we extrusion along this curved mesh. So this is a curved tunnel, okay? And right now, this tunnel is in the model pane. If we click this tunnel, we can assign, for example, a constant model to this tunnel. For example, we assign a Moore-Coulomb model, okay? And then we can have some information in the console, okay? Next, we set a material database, okay? For example, we have Moore-Coulomb database from the standard unit in kilopascal. I want this tunnel to be, for example, just low plasticity clay, okay? We add to the working set, close, and then next we set model properties, okay? We already add this clay, low plasticity. Click that, copy to property, and then save change. We can see that the information here, all this material property already assigned to the Moore-Coulomb model, okay? Very important is we have all these, state record already, yeah? We can copy this record, for example, to a data file, and then we create a new model data file, for example, this one. Then we add a new line, model new, and then copy that, operations. So we can duplicate what we did, in the sketch pane. So you can see we created this curved tunnel. Okay, this is my demonstrations for the new user interface, plot atoms, curve sketch, and material database. So let's go back to the PowerPoint. Let's go back to the duplicate. Okay. The next update is Python. So Python in FLAC3D is not new, but in FLAC3D version 9, we updated this Python version to 3.10.5. We have a lot of included Python libraries. So with Python libraries, it's super easy for FLAC3D to do parametric study. For example, in these examples, we have the dictionary in Python. We have some pairs of the relative density and CSR. We have 3 sets of them, yeah. And then we're using these 2 lines to convert the Python variables to fish variables. And then we call common data file, cyclic, undrained, direct, simple shear. So we can do this, parametric study for many cases. Just one click to run. Okay, and we also can using Python library to post-processing the figures. Okay, I will show a simple examples. So if we open a project file called cyclic on drain. So this is just very simple Python master file. So if we run this, we will have 3 cases, all together. So we can see the first, the relative density of 30% with the cyclic response using the P2P sand model. Okay. It's done. So we change the second case with a 50% relative density. So the first figure is a shear strength versus shear strength. The second is a shear stress versus effective pressure. Okay, if the last case is with a 30% relative density. So if we look at the data file, we all output the histories to a test file. So without using the test file, go to the Python to post-processing the figures. So here is an example of the data file in Python to plot. So we import some libraries and then using some, here is a read, load the test file created in the FLAC3D. Okay, and then maybe just a few seconds we can. So right now the model is done. So we can plot the figures just one click. For example, this file. Then we have all 3 cases plot and also with some summarize for the 3 cases. Okay, this just one example to show the Python in FLAC3D. So let's go back to the PowerPoint. So this is not new again in version 9, but it's our first time to have detailed documentation on the speed on multi-threaded fish. So we compare different methods, for example, loop, while, for each, and the splitting and the operators. So we can see that using the splitting and operators, it's much faster. So we recommend in version 9 using fish splitting and fish operator as soon as possible as you can. So we again in version 9 we have one more option for Timoshenko beams. So we have the option to show the beams is based on the Euler Bernoulli beam theory or Timoshenko beam theory. So for Timoshenko beam theory actually is considered a short and a thick and a beam. And for classical, it's considered a long and a thin beam. And in FLAC3D version 9, we added another damping model called Ramberg-Osgood Hysteretic damping. So the drawback of the current constitutive model and Hysteretic damping, the problem is that the damping at high shear strain is close to 2 over pi. That is more than 50%. But actually, the experimental data is usually between 20 to 35%. So this new Hysteretic damping model is to overcome this drawback. For example, there is a simulations using Ramberg-Osgood model. So we can see that the damping ratio at a high strain is very close to the experimental data, and similar for the G over G max curve, that's very close to the experimental data. So let's now switch to Jim on the zone joint.
Okay, we're getting near the end here. I've got 2 more features to talk briefly about. first one is something new that I've put into FLAC3D 9, and we're calling this zone joints. And what this is an alternative to the existing FLAC3D interfaces. So for those of you that are modeling rocks, and you're trying to simulate faults or joints or discontinuities, you may have used the interfaces before. This is essentially a new, more accurate formulation. As you may be aware, the interfaces that exist in FLAC3D 7 are one-sided. The new formulation is essentially two-sided interfaces, so you have a true contact between the two sides of the discontinuity. And the reason this is useful is when it comes to where you have multiple intersecting joints. The two-sided interfaces give you a more robust and more accurate representation of what's happening where you have those intersections. This is relatively new functionality for us. Right now, it's only working in small strain. Our plan is definitely to roll this out to large strain at some point in the future. Our goal here is also to make it as seamless as possible for people that are using interfaces. So the way to use these things is essentially exactly the same as you would do with interfaces. You just use keyword zone joint instead of zone interface. You can build these things from griddle models. You can build these things by separating groups in FLAC3D exactly like you would do with interfaces. So the next slide, this just shows a simple example. This is actually a model of an open pit constructed with griddle. There is material there in the open pit that I cut away just so you could visualize the joints better. So you can see the expression of the joints on the surface on the top plot, and then you can see the joints themselves in the bottom plot. And these are colored by friction. So there's one weak joint with a friction angle of like 20 degrees, and then some other intersecting joints with a friction angle of 30 degrees. And so if we go to the next slide, yeah. So if you excavate the pit and you let it run, I mean, this was a simplified model. We just did it in one shot, but what you can see is the pretty serious deformation along the joint, the weak joint there, that 20-degree friction joint, which is pretty much what you would expect, but it's just encouraging to see how it's behaving sensibly at these intersection points where these joints come together. And the bottom right here is just showing you the normal stresses on the joints, just demonstrating how you can plot all of the quantities on the joints like you can for interfaces. So, you know, normal stresses, shear displacements, and so on. And so, yeah, that's what I'm going to say about zone joints. And then the last feature I'm going to talk about is, you know, this is maybe not for everybody, but it's certainly useful if you're doing these nuclear waste type of studies. And what it is something we took from 3DEC and put into FLAC3D, and it's the fast analytical temperature calculation for specified sources. So if you can assume that your material is infinite in extent and isotropic, you can calculate the temperature at any given time for any given set of sources analytically. And why you would want to do that is because it's super fast. And so again, especially in these nuclear waste type problems, when you want to calculate something out at 1 year, 10 years, 100 years, 1,000 years, and you maybe have a whole bunch of sources, you maybe have canisters or something like that, and they may be decaying at different rates, we can consider that. So you put in all your sources, you put in your decay rates, you put in the time at which those sources are in place, and then you say, okay, give me the temperature at all the grid points in the FLAC3D model at these given times, and it will basically calculate that instantly. There's no calculation steps required. The calculation is essentially instant. So this can be attractive in a lot of situations. And if we go to the next slide. And again, once you have the temperatures, then you can use that to calculate deformations with a sort of one-way coupling approach. So you calculate the temperatures first, and then you can calculate the deformations. This just shows a relatively simple example of something that might be a nuclear waste repository. These little blue spheres are the sources. You might have a whole bunch of these canisters in place here. And then the contours are showing you the temperatures that result at some given time. And then you can see exaggerated deformations that might result from those increased temperatures. Okay. All right, that's pretty much it for new features. Just a couple of slides to finish up here. We wanted to emphasize a couple of things. We try to keep things flexible. We've increased the number of zones that you can use in the demo version. So this is the free version that you can download from the website and just use it. It used to be 600 zones, it's now 1,000. We want to try to encourage people to do this, to download the demo version, to try and make things and play with the program. 1,000 zones allows you to make something sort of realistic. You can see an example here in the bottom corner. This is a slope with less than 1,000 zones. It is approaching something fairly realistic. And the hope is that people will use this, especially in a classroom setting. Everybody could just download it and use it and get to grips with the concepts without having to, worry about buying a whole bunch of licenses. When you do buy a license, you may or may not know we now have web licenses that allow you to run the software without having to plug in a dongle, which is very nice. And all of the licenses allow you to run 2 instances on one computer. So you could have either 2 instances running at the same time, or one running and one playing around with plots or whatever you want to do. And then the last bullet point here is just related to looking at models on remote desktop. There used to be a few issues if you had started the model in front of the computer and then went home and logged into it with remote desktop, weird things would happen. That's all been resolved. So now it's completely seamless. If you're sitting in front of the computer or if you're using remote desktop, that all works perfectly well. And then I think this is the last slide. Just something about what's coming soon. So I mentioned before that the implicit fluid solver is only working for fully saturated fluid. We actually do have it working for partially saturated fluid. We just have to roll that out. And as part of that development effort, we also simplified and tried to make it easier for people to do these types of fluid flow simulations. So the whole sort of fluid flow logic has been overhauled somewhat to make life easier for people. They're trying to do these fluid-only simulations and also coupled simulations. So not only will it be significantly faster with the implicit solvers, it will be easier. Second bullet point, we're partnering with a company called Rescale to make it easy to run FLAC3D on the cloud. Essentially, you just log into Rescale, and FLAC3D will appear as tiles that you can click on, and it's really easy to start FLAC3D, and it will just go off and run in AWS or Azure or whatever. These are actually running on Linux, and the reason you would want to do that is because it's significantly cheaper than running on Windows. There's really no difference between the Linux and the Windows. You can even take a Linux save file and restore it in Windows and look at it. So the attractive proposition here is that you could run a bunch of things on the cloud and then take those save files and look at them on your home computer on Windows if you prefer to do that. And then the last thing to mention, you may or may not be aware that we've been working on a 2D version of FLAC3D. It's actually out there already in a pre-release form, so a public beta. You can get it now. The actual official release will be in June. And the purpose of this is just to try to make a more consistent user experience for people that are doing both 2D and 3D. If you've used FLAC before in the past, you will have noticed that it's quite different than the existing FLAC3D. Our plan was to bring these things more together so that it's a much more consistent experience. And if you want to try out FLAC2D, you will see that the commands and the fish and the plotting and the interface and the look and feel is all the same as it is in FLAC2D. And so that's coming out in June.
Okay, great. Thank you, everybody, for participating. Thank you for the presentation. We have some links here, and we will be providing a PDF of the presentation, so you'll have a document that you can click on to link to these things, but we just want to point out, obviously, if you are interested in getting a sales quote, we're going to make a 2-week trial available to everybody who's registered for the webinar, so there's information about that. Just a reminder, we have our software forum, our software academy for training courses, and as always, if you need